Hi, my name is Michelle, and I am teaching a lesson on get this right, the TPRS method, and I'm teaching students that are beginners, and we are going to work on questions and statements today. So welcome, class. We're so glad you're here today, and we just talked about what we did over the weekend, and it sounds like you guys did some really fun things. So today we're going to talk about either is it a question or a statement, and how do we know the difference? And with questions, we have a big question mark, and with statements, we can have an exclamation point or just a period. So, but today we're going to work on questions, and my question for you today is, I'm going to write it right here. Are you my mother? No, put a little question mark. Are you my mother? No. Well, I have a really fun story we're going to read, and then we're going to do some activities related to this. So we are going to read the book, Are You My Mother? A mother bird sat on her egg. The egg jumped. Oh, no, said the mother bird. My baby will be here. He will want something to eat. I must get something for my baby bird to eat, she said. I will be back. So away she went. The egg jumped and it jumped and it jumped. And out came the baby bird. Look at the baby bird. Where is my mother? He said. He looked for her. He looked up, he did not see her. He looked down and he did not see her. I will go and look for her, he said. So away he went. Down out of the tree he went. Down, down, down. It was a long way down. The baby bird could not fly. He could not fly, but he could walk. Now I will go and find my mother, he said. He did not know what his mother looked like. He went right by her and he did not even see her. He came to a kitten. Are you my mother? He said to the kitten. The kitten just looked and looked. It didn't say a thing. The kitten was not his mother, so he went on. Then he came to a hen. This is a hen. Are you my mother? He said to the hen. No, said the hen. The kitten was not his mother. The hen was not his mother. So the baby bird went on. I have to find my mother, he said. But where? Where is she? Look, that's a question. Where is she? Where could she be? There's another question. Then he came to a dog. Are you my mother? He said to the dog. I am not your mother. I am a dog, said the dog. The kitten was not his mother. The hen was not his mother. The dog was not his mother. So the baby bird went on. Now he came to a cow. Are you my mother? He asked the cow. How could I be your mother? Said the cow. I am a cow. The kitten and the hen were not his mother. The dog and the cow were not his mother. Did he have a mother? What do you think? Do you think that little bird has a mother? Yes, he does. I did have a mother, said the baby bird. I know I did. I have to find her. I will. I will. Now the baby bird did not walk. He ran. He ran. Then he saw a car. Could that old thing be my mother? No, it could not. The baby bird did not stop. He ran on and on and on. Now he looked way down and he saw a boat. There she is, he said. The baby bird called to the boat, but the boat did not stop. The boat went on. He looked way up in the sky, and he saw a big, huge airplane. Here I am, mother, he called out, but the plane did not stop. The plane went on. Just then, baby bird saw a big thing. This thing must be his mother. There she is, he said. There is my mother. He ran right up to it. Mother, mother, here I am, mother, he said to the big thing. But the big thing just said, snort. Oh, you are not my mother, said the baby bird. You are a snort. I have to get out of here. But the baby bird could not get away. The snort went up. It went up, way up, and up and up and up went the baby bird. But now where was the snort going? Oh no, what is the snort going to do? Do to me? Get me out of here. Just then the snort came to a stop. Where am I? Said the baby bird. I want to go home. I want my mother. Then something happened. The snort put that baby bird right back in the tree. The baby bird was home. And just then the mother bird came back to the tree. Do you know who I am? She said to her baby. Yes, I know who you are, she said the baby. You are not a kitten. You are not a hen. You are not a dog. You are a cow. You are not a boat or a plane or a snort. You are a bird, and you are my mother. Okay, so now, hold on. Now we're going to play that. So we're going to have one person come up into the front of the room, and they're going to go around and ask everybody, are you my mother? And then that person is going to say, no, I'm not your mother. I am a tree. And then it looked like a tree or whatever object or thing you want to be. So we will do that game, and then we'll be back. Thanks. That's it for today. Okay, I'm in the middle of recording something. Don't stand at the door. Oh my gosh, you totally threw me off. Yes, you can have that.
Okay, I was just wondering. I was about to point just so you could see.
Yes, when I'm recording myself for a lesson.
Sorry.
Hi guys, welcome to lesson 10. I noticed we had a poll before class started and asked how you were feeling about the prepared material, and I think everybody said that they were having trouble with it. So I'm going to try and smooth over things in this meeting here, and then if you have any questions, please throw them out here. I'll try to cover it a little bit more in depth. Hi Evelyn. I'm glad to see some of these people here so that we can talk about these things. So this week's class meeting, this week's class meeting isn't going to be as fun as last week's. We started learning about concepts that I think are a little bit more complicated than anything we've learned so far. So we are going to review some of that. It's hard to do chemistry, all the things that we talked about in chemistry in just a couple of weeks. So I want you to know, we have been working on improving this course and maybe easing up a little bit on the chemistry, but I'll do my best to prepare you for the quizzes and the tests that will be on this stuff. And I'll let you know kind of what you'll be tested more on.
I have to make a nutrients dinner.
Before tonight?
We're also going to talk about
It's not
how
happening. I just
No,
didn't
for
know.
me to take there.
how their structure affects
On the
their
hike?
function.
Yes, because we're gonna stop in
So
somewhere.
it's going to be a lot for this next 20 to
Just
30
7
minutes.
Yeah, and that's the nutritious, on your hike, that's nutritious dinner.
Anything else?
An orange, a banana.
I'm going to start with a prayer because I think we can use all the
No, I have a piece of chicken.
I can't do white bread,
I'll do that
please,
never
bread.
jump in.
Why can't you do white bread?
It's not nutrient.
You can do a croissant.
We're so thankful
It's
for
gotta be
Okay, you're not. No, my bread's expensive, and you're not gonna like it.
learn
You
about
choose white bread. It's fine.
chemistry and
It's not that unhealthy.
learn about all their wonderful creations. And we ask the blessings that we can have the Spirit with us, that we can understand these concepts and start to apply them. We love you very much, and we're so grateful to have this opportunity. Do the things So, Richard Feynman, he was this incredible guy. He won the Nobel Prize in Physics in 1965. He was also involved in the science behind why the Challenger explosion, that catastrophe happened, and he kind of predicted something, and then found out that that's what really happened. I'll post more about that in the Explore board. I have like a link about him that you guys might find interesting, but he also said this really cool thing. He said, if in some cataclysm, all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe that it is that all things are made of atoms. So why would he say that? There's a lot of things that we could choose, and I'm sure this is a matter of opinion. In fact, I asked this question in our Explore for this week. What would you choose to be the sentence passed on to the next generation? But I think he said that because all things are made of atoms. We're starting back at the smallest level. And if we can understand the building blocks about how things are made, we can start to make predictions about larger things. If we can understand how things are structured, then we can start to know how they can function and how we can change that function and use it for our benefit, which is a big thing. Because that's what chemistry is. It is a study of three things. Sorry, I have a cold. What things are made of, how they interact, and how we can use their properties to make new things. Because chemists and basically the entire world, they think that substances are made up of a bunch of little particles. And these particles are either molecules, and we should recognize molecules every day. These are things like lipids, which is fats, like using vegetable oil, that's a molecule. Carbs, amino acids, or the particles could be ions, like salts and soaps. Or atoms, like metals. Atoms generally means something that's made up of just one element, like diamond is made up of carbon. And these little particles interact with each other in different ways to determine their properties. So we kind of talked about this last week, but I want to talk about what atoms are actually made of. First of all, there are three particles that make up an atom. Can anybody tell me what they are? See if I can pull up this picture here. Yeah, here it is. Like everyone's typing. So there are three particles, and they are found in different locations in the atom, which is what Rutherford was figuring out. Proton, yes. Awesome, guys. So proton, electron, and then also a neutron. Yeah, perfect. Are the three things, and their names tell us a little bit about them, in that they have charges. So the protons and the neutrons are in the nucleus, and then the electrons are around the nucleus. They're kind of zipping about. And protons are positive. Neutrons don't have any charge, so like neutral, right? And then electrons have a negative charge. And these particles also have different masses. So it's interesting, but the particles with the greatest mass are in the nucleus. That's protons and neutrons. And electrons have just the tiniest fraction of the mass of protons and neutrons, and they're the ones that surround the nucleus. So then, what we understand about positive and negative, would they then be attracted to other similar particles? So positives are going to be attracted to negatives. The protons of one electron are going to be attracted to the electrons of another one, which is what brings atoms together. Atoms stick together because their charged particles are attracted to the oppositely charged particles in other atoms. And that is one sentence that explains everything around us. All of these atoms sticking together to form me is because of these charged particles, which is kind of crazy, right? So the prepare assignment talked about covalent bonds a little bit, and there are a lot of different charges at play here, and determining how close together these atoms are is the protons and the electrons of these atoms. So the electrons of two atoms are both negatively charged. So you would assume that they repel one another, right? But at the same time, they're interacting with the nucleus that's positively charged. So as two atoms come together, they're being attracted to one another, but they get to this point where if they get too close, the protons kind of repel them a little bit. So there's this perfect balance where the lowest energy is what describes how two atoms interact with each other. There's this perfect balance where the protons are pushing away too much and the protons and electrons are pulling each other together. And that distance is what changes between different elements because they have different numbers of protons and electrons. So they have different amounts of charge. So the reading has a detailed description of what's going on here, but I think this is boiling it down to its basics. And so covalent bonds are where the electrons are pulling with the protons so tightly that they're pretty close together. The bond is pretty strong. And I'm going to talk more about electronegativity. So the way the periodic table was designed, maybe some of you guys chose this for your story behind the science article, which is really good, but it's been designed in a very interesting way. It's been arranged so that there are certain patterns of chemical properties that can be inferred based on their location in the periodic table. One example is electronegativity. There are other examples. So electronegativity is basically a number that indicates how much attraction an element has for the electrons. A more electronegative element wants other electrons more. So numbers are assigned to each element to help us understand how they will be shared between the two elements. And so the larger the difference in electronegativity, the more the electrons will be pulled to one side of the bond. So because one element wants some more, so they're going to take the electrons more from the other element. You'll notice that electronegativity increases, sorry, this is backwards. So it increases across the periodic table. That's because as we go across the periodic table, we're getting more and more protons. So the more positive charge, the more it wants negative charge, the more it wants electrons. So that makes sense, right? And then as we go down the periodic table, the elements are getting bigger. The more large an element is, the more levels of electrons it has outside of it, shielding that positive charge. So the electronegativity goes down because the electrons from another element can't feel that positive charge as much. So that kind of explains why we see this trend. So covalent bonds are when atoms share electrons, and there are two types of covalent bonds. There are polar and non-polar covalent bonds. You're going to have to know, trying to think of the best way to organize this information. We're going to talk about three different bonds: covalent, and within covalent there's polar and non-polar, and then ionic. And the way we decide what type of bonding it is electronegativity. So just because electrons are being shared in a covalent bond, it doesn't mean they're being shared equally. Let's look at a hydrogen fluoride molecule. So hydrogen, let's see if I can pull it up here. Hydrogen is, kind of pull a pointer, but it went off to the weird side of the screen. Okay, so hydrogen is purple and it's at the top, and it has an electronegativity number of 2.1. So fluorine has an electronegativity of 4. It has way more protons than hydrogen does. So which one would want more of the electrons when it's sharing this bond? What do you guys think? Just put H or F in the chat box. Yeah, perfect, Eliza. That's right. So the fluorine has more protons, is more electronegative. So when hydrogen and fluoride make a bond, more of the electrons are going to be pulled towards the fluoride. Whereas if it was, say, a hydrogen and carbon bond, 2.1 versus 2.5, they're more similar. They don't want, one of them doesn't want the electrons that much more than the other, so they would be more non-polar. The sharing would be more equal. So when we're talking about covalent bonds, they're sharing electrons Polar is not equal sharing. One of them is a little greedy. It's more electronegative. Non-polar is where they share more equally. This kind of shows a picture of that. So there's 3 different types of bonding like we talked about. Non-polar covalent are formed when there's small difference in electronegativity. Polar is when there's a moderate difference in electronegativity, like the hydrogen fluoride one that I talked about. So one of the atoms pulls more of the electrons. That circle around it is considered like the electron. So you'll notice that it's bigger around the fluoride. They're kind of pulled more towards the nucleus of that element. And then in ionic bonding, one of the elements wants the electron so badly that it just takes one. And so they're kind of still held together because they like each other, because then one of the elements is positive and one of them is negative. But one of the elements took all of the electrons. And so there's a continuum of polar, non-polar, and ionic bonds, and each bond will kind of fit in this continuum somehow. So there's going to be some elements that are more polar covalent than others, but they're still considered polar covalent. And that's about all you need to know about bonding, is know the differences and know the definitions. What is non-polar covalent? You would have to put equal sharing, that kind of a thing. Does that make sense? Does anybody have any questions about different types of bonds? Okay, let me know if you do as we go through this. So why do we care? I mean, why does the scientist care? Maybe you guys don't care as much. Knowing the type of bond allows us to predict a lot about the molecule's properties. A simple example might be whether or not something dissolves in water. If something dissolves in water, it's called hydrophilic, philic meaning love, so it loves water. And if it doesn't, it's called hydrophobic. And you'll notice when you have Italian dressing, there's the oil that sits on top and then the watery substance that sits on the bottom. That's because oil is a nonpolar bond, and because it's a lipid, we'll talk about that a little bit later. And it doesn't like water, so it won't mix with it. So whereas sugar is a polar bond, it's between oxygen and hydrogen, which oxygen is a lot more negative, electronegative. So it will dissolve in water because it's polar. So that's just one example. Other examples might be the stronger a bond, the more covalent a bond is. The harder it is to break up those molecules, and so it might have a higher melting point because it takes more energy, more temperature to actually pull those molecules apart. Things like that. So in the prepared reading, it also talked about valence electrons. And I'd like to do some examples of Lewis structures to make sure that you guys understand how to do that, because that will be on the test and in the quiz. So each element, except for hydrogen and helium, and then the ones in the middle, act kind of strange. So hydrogen and helium just want 2 electrons. All the other elements are trying to get to 8. It's called the octet rule. It is just where they have the lowest amount of energy, there's the most room for 8 electrons going around their nucleus. And based on where they are in the periodic table, we can know how many electrons they have, and then which elements that they will react with to get up to 8 electrons. So, like, carbon is in this 4 section, so we know that it has 4 valence electrons. So it wants to make bonds with either 4 other elements or one element that also needs 4. And so I'll kind of show you. Let me pull up the whiteboard and do a couple of those structures. Okay, so when we think about carbon, let me just do my on here. So carbon has 4 valence electrons. How do we know that? It's because we look at the periodic table, we see that it falls in that group that always has 4 valence electrons. So when we're doing Lewis structures, we draw those electrons and we do 1 on each side, like that. Or I can't make a perfect circle on this whiteboard very well. So then, if it were to interact with something like fluorine from the periodic table, sorry I don't have it up, fluorine has 7 electrons. So how would we draw that? We draw 1, 2, and we do it on each side, and then we start doubling them up. Can you guys see that on the whiteboard? Let me know if you can't see it. So that's how you would draw that's how you draw a Lewis structure for fluorine. So we see that fluorine has one extra spot for an electron. So it could potentially interact with carbon and take up this side here. And so this would turn into a bond. Now they're sharing these 2 electrons. But carbon still wants to make some bonds. It's not done because it still has these open spots. So if it were to interact with fluorine again, then it would fill up this spot, and then it would fill up this spot, and it would end up having, fluorines all the way around. Because fluorine will always have one spot open to share with, right? Let's see if I can take off these off. Okay, so what if carbon was to interact with, say, oxygen? So oxygen has 6. So we do 1, 2, 3, 4, 5, 6. So oxygen still has 2 open spots to interact. It might interact with one carbon here, right, and form a bond. And then it might interact with another carbon here, or it could interact twice with this carbon, and they will fill up 2 of their spots and create a double bond. So then we would have carbon double bonded. This is how it looks. But all the extra work was on there. And now carbon still has 2 spots available. It could bond with another oxygen, right? Because it has 2 open spots. Carbon has 2 open spots. It could also bond with one of those fluorines. And maybe hydrogen. If a hydrogen it's kind of different. It only has 1 electron, but it only wants 2. So you'll see a lot of hydrogen in chemical equations because it's very abundant, and it makes an easy bonding because it has just 1 spot. It'll just fill up 1 electron sharing location, 1 bond. So that's what a molecule could look like. Does that kind of start to make sense? So if I were to ask you a question like, carbon wants to bond with hydrogen. What's the most likely formula for it to look like? Would it be CH? Would it be CH2, CH3, or CH4? What do you guys think? What would be the answer there? This carbon has 4 open spots, and hydrogen only fills up 1 of those spots. The most likely thing that would happen would be, yeah, CH4. Yeah, so that's about the extent of how you guys are going to need to understand these chemical reactions. Does anybody have any questions about Lewis structures before I move on? It's basically just practicing going around the element and putting electrons on. And the way you know how many valence electrons it is you're not getting it? Okay, well, do you have what part? Just whole thing. I know it's a lot. I know it's big. Basically, elements want 8 electrons. We know how many electrons they have based on where they're located in the periodic table. And so based on how many they still have, where CH4 come from, let me draw that one. So carbon, we know it has 4 valence electrons based on where it is in the periodic table. Yeah, perfect, Ari. Yes, that's right. I didn't explain that very well. Thank you. So carbon, we know it has 4 valence electrons because of where it is in the periodic table. So we can draw that. Now carbon wants 8 electrons, and all it has to interact with in this example is hydrogen. So if we have hydrogen, which only has 1 electron, but it's one of the special ones that only wants 2. It's going to interact with 4 different hydrogens because it can make a bond here with this one, but it still has these 3 open locations. It's not happy until it gets 8 electrons. So then it's also going to interact with this hydrogen. It's also going to interact with this hydrogen. So if carbon is interacting with hydrogen, it's going to interact with 4 hydrogens because it can only make 1 bond with each one. you would see the same thing if it was interacting with fluorine, because fluorine, we know from the periodic table that it has 7. We do 1, 2, 3, 4, 5, 6, 7. It still has 1 electron here that wants to make a bond. So if carbon was going to interact with fluorine, it would do it 4 different times. We would see C4, CF4. So in H2O, there are 2 hydrogen atoms, oxygen atoms. Yeah, perfect. So, yeah, that's right. So, let me see if I can, I'll just draw it down here. Okay, so we have oxygen. We know that oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. It has these 2 open locations, which is why we see H2. There's 2 H's, right? So we make a bond with an H here, and a bond with an H here. So that's why we see H2O so often, because oxygen has 2 spots for hydrogen. Why doesn't hydrogen want 8 electrons? It's a really, really small element. We could get into quantum mechanics, but basically they just have one shell that just has room enough for 2 electrons because they're so small, which is why helium also only wants 2 electrons, but it automatically only has 2 electrons, because they are both smaller elements. They're the ones that, if you remember from our astronomy unit, they were cooked very, very quickly because they're the smallest, and so that's what we see in the universe of hydrogen and helium. So does anybody have any questions about this? Does that make more sense, Lori? Okay, great. If any of you guys still have questions after this class meeting too, send me a quick email and we can try and go over it. It might be something that you'd want to practice too. Unfortunately, at least we're making progress, right? It is tough. That the CH4 and the CF4, that's the most complicated question that you can get. I think. I'm trying to think of anything more complicated, but I think that's about it. And I have more material here, but it's more to illustrate the point that structure determines function. So I don't want you guys to get overwhelmed with it. I'm just going to go over one example. Well, it's a lipid example. I'm going to talk about the lipid one. So lipids consist of only carbon, hydrogen, and oxygen. So for the most part, they're very non-polar molecules, which is why we see that they're hydrophilic. One interesting thing is you'll notice on your food that you'll see saturated fat, unsaturated fat, and trans fat. So unsaturated fat is most healthy, and that's because the way it is formed is there's a double bond in there, which creates a kink in it. You can see, you can kind of see it in this bottom right-hand picture that there's a kink in it. And so it doesn't stack very well in your arteries. Whereas trans fat, it also has a double bond in there, but the way the double bond is, it makes it look like saturated fat. And those saturated fats form these long, perfect chains, which just like to stack up in your arteries and cause heart disease and things like that. So I just wanted to show you this example to show you that the way chemicals are formed and structured drastically affects how they function and how they affect you. So that's kind of just one of the points of the class. I wanted to make sure that we got through that and then also left some time for questions. So what would help you guys the most? Do you want to go over more examples of how molecules interact with one another, or elements interact with one another? Do you have questions about bonding, Lewis structures? Would it help if I gave you some practice questions and an announcement or something? Just post those online. Practice questions, please. Okay, yeah, let me find some practice questions and I'll post them in the announcement that has a class meeting. And then I'll also post answers. And then if you have any questions as you're filling out those, filling out the practice questions, please just email me and I will try and explain it in a different way. I know everybody learns differently. Sometimes it helps to try a few different methods. Yes, I will post the PowerPoint also. Thank you, Kelly, for reminding me, because I actually fixed that.
Hi, sweet pea.
But just know that it is totally normal to have trouble with this material. It's basically the first couple months of an intro chemistry class kind of boiled down into 2 weeks. So we kind of touch a lot of topics, but just the surface of them. No, for the discussion board, you never need to answer all the questions. You can I just want you to have something to post about, so I offer you those questions. But you can choose one, you can choose long, you can choose something else, whatever you want. I would also love if you've had any questions to post them to the Explore discussion board. Maybe somebody else in this class can answer this question for you, and also I'll see it, so I can answer.
Are you poopy? We need to change your butt.
It's a great point. Eliza. Clear as mud. Good. Modularly is something, I guess. Really, it is tough material, and hopefully as
change
you
your butt in
this
just a
week,
minute.
you start to become more familiar with it. I think chemistry, as cliche as it sounds, it takes practice.
Hi.
Also, the prepared material talks about stereochemistry. It talks about isomers and things like that. That's where molecules are the same structurally, but they look different in space. Kind of like how my hands
I'll do it in a minute, or you can
made up of the same things, but in space they're not exact. They're not exactly the same. They're mirror images. That's what stereochemistry is. That's about all you need to know about it. Don't stress out about stereochemistry. Just know that it exists. I don't know why we still include that in this course. So that's something that I think would be important. Oh, awesome, Lori. Yeah. You know what? If anybody finds any good videos, post them, and I will try and, because we have different discussion board groups, I'll try and share them with the other group. I have found some good videos in the past too, so I will post those along with practice questions and this PowerPoint in the class meeting tonight sometime. Thank you, Lori. Okay, so I'm going to close this meeting. Again, please reach out if you need anything at all. Thank you all for participating and asking questions and being patient with this material. I know it's tough. So, yeah. Good night, everyone.
Comments, I think.
What you doing? Just make it. No, just. No, just make it. No, I just give you a kiss. Oh, who's that? Who is 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 that? Oh. Goodbye.
Hi there, what did you get? Molly! She's getting into trouble. We need to go pretty quick. I think she pooped. I don't think it's checked her. Are you doing it ready? You need comfortable, good walking shoes. You probably should wear shorts so they won't look at this and pull down. No, I'm gonna take your poopy butt again.
Yeah. No, you say.
Stop saying. No yelling. No yelling. Very good, good.
Oh.
Molly, that was stinky.
Did it do?
Okay, roll back over, sneaky butt. Yeah, you are sneaky butt. You can find some stroller shoes. Come on, Herman. You would love to look out. Okay, watch me.
Mom. You can't have it. You're too young. 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 Falling. No way to do that. Only if you want to close. What do you go? My hands are full. I'll be right back. I'll be right back. Here we go.
You come get her. Ah, she's gonna get you. She's gonna get you. Ah!
I got you. Oh, I didn't hurt you.
Let me. What are you wearing? Is that your pajamas?
Yeah.
Okay, put it down. Let me just soil out. You want that? Are you hungry? Let's find you something to eat.
I'm my mother. It says it on there. With us?
A little bit. Don't. Oh, I have to feed you? I have to feed you? No, this one.
I really hope I'm not in the same class as McKenna.
Why?
Because she makes such a job. Because one time
Well, she's got lots of friends. Seems like you're the only drama friend with her, or there's other friends.
with other people. Because one time, like there is
Okay, I'm trying to do this assignment. I'd like to hear what you have to say. You want to take her and feed her this? Now that you got coconut oil on. Okay, here, go. Go with Avery. She's gonna. You can sit right in that chair and feed her. But I just got a little bit more on this assignment to get done.
Hey. Okay. Cheese. Yeah. Finish that piece first. Okay, just showing me that so fast. Let's come get that. You can't be that hungry. Oh yeah. No. Yeah, okay. I'm watching this magic about the rice and learning.
Yes. Why don't you have a hot dog?
I can't find the hot dog.
You put them in the fridge.
I know.
Okay, you go find them. They're there somewhere. No one walked off with them. Okay, then find something. You had them. Look for them a little better. You just open the fridge. You look a little bit better.
The only reason she started crying was because she smashed her fingers. And they're not there. Molly, you can't just keep on getting out the top line. You can't just keep on getting these out. No. Let's go. Give it to me, please. Give it to me. They're not there.
Up. You want more stuff? You like cheese?
She's fine. When are you gonna be done with math?
Math?
Whatever you're doing.
I don't know why.
Cause. What are you doing, Molly? Yeah. Oh, you look so cute. You look adorable. You look adorable. Stella. Molly, we can have graham crackers, but you can't keep on getting this. Oh, Molly. Oh. Hi. You know what? Take that.
I know. You give those to me, but
Whenever I try to,
we're graham cracker.
I was trying
Have some
to.
more graham crackers. That's better. I don't know why noise.
Oh! She wants to see what I'm doing now. Don't know how to open this thing.
Look and see if there's something in the cupboard first, maybe. Or in the pantry first. Open.
No, wait. Molly. Give it back. Okay, put that. You can shake it. You can shake it. Oh!
Okay, take it and go get started on it.
Okay. I can't do anything about that.
Yeah, you're gonna have some mac and cheese with. Hurry and start it because she will eat some of it. So hurry. She's hungry. Okay, just a minute, and we'll get you some. Okay? Yeah, Tia's or Avery's gonna make some mac and cheese. Okay?
Molly, you. Molly, that's you. Where are you going? Why are you keeping going, Grandma? You're so mad that you're stuck with me.
Ah, she's making you some mac and cheese.
Okay, okay.
Dad.
She's still dropping it. And she's. Here, I can have it. Here. Here. Here, Grandma.
Oh my goodness! Oh my goodness! Oh my goodness! What's going on? Huh? Is that Mia? That's Mia, your friend Mia. Mia. Yeah. And that's a giraffe. Giraffe. All right. So watch your noodles. Yeah. You want that noodles? You hear the doggy?
Let's go find the dog. Yeah. Go find the dog. Where's Mom? Welcome. Okay, you do it.
You just ignore that. Molly.
She was watching a show and then she started moving my phone. And then I said, just leave it, and she started crying.
You don't let her cry like that. Just do what you need to do. Does that make sense? She's throwing a fit. She's learning tantrums. So don't give in to her tantrum. Don't let her win that tantrum.
I know. I kept on saying, sit down and I'll give it.
Okay. And
Put
if she
it down.
doesn't,
She's just like,
I know, it's okay. She's not going to get in trouble if she's screaming.
Molly. Hey, okay.
Yeah. Yeah, that's Mia, huh? No. No. No.